We're live. What?
They can't see my head.
No, what they see is what is in the screen there.
Oh gosh, my head is bigger.
Oh, wow. That is. Does anybody sit there in this period? You can move up if you want. If you want to do that. So Ellie's going to move because otherwise her big head's in the way. I don't think anybody sits there this period. Yeah, that's where Savannah sits. And that desk is clean because I cleaned. No one sat there during advisory, so it's already been hydrogen vital oxided. Hi, how's everybody doing? This is the big class. This is my biggest class out of everyone. And what is it, 10? Did I just count 11? Yeah. So. Child, was that you I saw this morning? Did I see you this morning? I said hi to this person, and I thought it was you. And I was just zooming past them, like walking 100 miles an hour with 3 other people. Yeah, and this person walked by, and I thought it was you. I was like, hey, what's up? And they just kept going. And I was like, well, maybe that wasn't her. Okay, so the 4 horsemen of the apocalypse. So just real quick. What the heck going on? Oh, that's a Zoom from last period. Gosh. Good Lord. So we're gonna have a test on Friday for you guys, right? So I made that up this morning. So it has. This is for you watching at home too. There's 4 problems where you just have to straight find the derivative of something. Okay. There's one relatively simple implicit differentiation problem. Maybe I can write this down. There's one related rates problem, and it's a pretty easy one. If you need the formula that is involved for that, I will give it to you. I probably should have just typed it on there, but I've already printed this. So there's one max-min inflection point problem algebraically, where I just give you a function, and then you find the local maxes, local mins, and the inflection algebraically. And it's a pretty easy function to work with. Like what would be an easy function to do that with? What type of function? Where you have to take the derivative and set it equal to 0 and all that? What's an easy function to do that with? Like would a trig function be easy to do with that? Setting a trig equation equal to 0? Maybe, but I think there are easier functions than that. Would an exponential function be real easy to do that with? Maybe, but I think there's easier ones than that. Well, linear would be too easy. Like, but you're in the ballpark. Like a polynomial, okay? So, and then you're going to have one question where I give you the graph of a derivative, and then you're going to answer questions about the function. Okay? And that's it. And you will have to know how to find the equation of a tangent line. Like, we did that a lot back at the beginning, and I felt like kids some of you just kept missing that over and over and over again. It's like, hey, this is a big idea here. You will have to know how to find the equation of a tangent line. So that's that. So you guys are going to do this on Friday, yeah? So all of your friends will be able to tell you what's on it from second period. Tell you all the answers. Yeah, you want me to live stream them taking the test? That'd be kind of funny. Just like a view of the board. Oh. And then somebody can be the thumbnail. Okay, so today, it looks like a lot of you watched yesterday. How did that work? Did that work pretty good? Like, was the sound pretty good? Like, could you see what I was writing on the board? I showed it to my wife and daughters last night at dinner, and my wife's like, I can't read what that says. And I was like, well, I think if you knew what it said, you would probably be able to read it. I think she was more like she didn't know what it was saying. It's hard. No, I left. Like she was, you know, she didn't know what all the. It's like if it was written in a foreign language, you wouldn't be able to read it. You know, it's. So, but yeah, hopefully that worked out well. This could be short-lived. I mean, I'm betting my money that we're going to end up online again. Like, I mean, Centerville made the decision last night to go online until January like 13th. Yeah, so. Well, I would see you on Friday. I mean, I don't think we're going to go online tomorrow. I think they'll give us a couple days. Finish out the week at least. But if we end up still being, you know, if you know things work, then we will do this live stream, and we'll do this live stream thing for the folks that are staying remote. And I think I have like 3 or 4 of those kids. So yesterday you learned L'Hopital's rule. Like we learned that in class yesterday. Okay, and that's where it's a technique that we use to find a limit when the limit is in what we call indeterminate form. And L'Hopital's rule only works for 2 types of indeterminate forms. Which ones are they? Do you know? If you were paying attention yesterday. Infinity over infinity is one of them. 0 over 0 is the other. Okay? So if you don't have infinity over infinity or 0 over 0, you have to somehow make that happen. Okay? And so what I want to do today with you is to do a couple of examples with you where you don't have that, but you still have an indeterminate form. And so we have to do some like algebra, like, and get it, rewrite the problem in a way so that we can use L'Hopital's rule. Okay? And then after that, I'll play you the song, maybe, if we get done. The song, yes. So there's, I talked about this in the second period yesterday, which I'm guessing you didn't watch the entire hour and 20 minutes of the live stream. But there's something out there called Calculus the Musical. And it's like a legit show. It's a real production that tours around the country. It's been to Fairmont. We've hosted them maybe 3 times, I think. The last time was like maybe your guys' freshman year. Yeah. Yeah, it's been a few years. I can't remember. But it's basically just, there's a little bit of a plot, a very, very loose plot, kind of about the development of how calculus came to be. And there are all of these songs that deal with calculus concepts, and the songs are parodies of other songs. So like popular songs, like there was a Lady Gaga. They've added some new songs and they've taken some old ones out. Like there was a Lady Gaga song once, and but the L'Hopital song is like, that's like, when you think of Calculus the Musical, you think of L'Hopital. Like, it just, you'll see. So let's just jump in here and do a couple of these, okay? This is one of my faves because you've seen this limit before. This was on the 1 to the infinity. Okay, so you guys remember that from yesterday? That was probably in your notes. And now we know the answer to this. Do you guys remember what the answer to this is? We talked about it in class yesterday, but it's E. So somehow, in some way, this function, 1 plus 1 over x to the x power, as x gets huge, is approaching the number E. Okay? So just to make sure everybody's clear, that's taking on the form 1 to the infinity. Okay? Does that make sense? We see how that came from? So now we've got to do something here to get this so that we have a fraction and we can use L'Hopital's rule. All right? Now, there's a strategy that's involved in doing problems like this when you have like x's in the exponent or functions of x in an exponent. Okay? And the way you do that is using a technique called doing it logarithmically. And I cannot remember if I taught you logarithmic differentiation or not. Like, I cannot remember if I did that or not. I have this like vision and like memory in my mind of standing here behind that glass talking about it. But I don't remember if I just told you that it existed and I never taught it to you, or we actually did it. I cannot remember. So if we did do it and we did examples of it, this is going to seem very familiar, okay? So what I'm going to do is I'm going to say that L, I'm just conventionally using the letter L. I'm going to say that L is the answer to this problem. I don't know what L is, but it's the answer to this problem, okay? And so what I'm going to do is I'm going to solve this problem, not for L, but for the natural log of L, okay? So you might think, oh, I'm just going to take the log of both sides. Okay? And so I'm just going to keep writing the natural log of L here on the left side. We'll just keep writing that. Now, right here is kind of a weird step involved in this problem, and that is if I'm taking the natural log of this limit, since things are pretty much continuous after x equals 0 here, I'm allowed to say that's equivalent to the limit of the natural log of all that. You can interchange those. And maybe after we're done with this problem, I can do a separate example of show you why that kind of works the way it does. It's once you see it, it's not too terrible. Okay, so I'm still needing to compute this limit. Now this isn't, right now at this point you're saying this isn't helpful. Like, we still have 1 to the infinity here, right? We just have now a natural log involved, okay? We still have this 1 to the infinity thing here going on. All right, but I'm going to take advantage of something because I have the natural log of this raised to a power. What are you allowed to do with that x? You can bring it down front. Now I'm one step closer to being able to write a fraction. Okay? And now we did this yesterday. Can I write that as a fraction? How can I write that as a fraction? That x natural log of all that. This is what we did this little trick yesterday when we multiplied by x and natural log of x, I think. What did we do? Yeah, we rewrite this as the natural log of 1 plus 1 over x over either over x to the negative 1 or 1 over x. Do you see how these are? This right here is equivalent to that. That's going to involve your algebra pans, okay? You guys know about algebra pants, right? Okay, so let's just pause for a second and look at what we have. Okay, I'm taking the limit as x goes to infinity, yeah? As x goes to infinity, what's happening in the numerator? 1 plus 0. What's the natural log of 1? Oh, you're going to make me cry if you can't tell me that. Like, I'm going to cry over the internet. Like, the entire world could view me crying right now because my students in Calc 1 can't tell me the natural log of 1 just off the top of their head. But if I said, what's the square root of 4, you could all be like, oh, that's 2. But you can't tell me the natural log of 1? E to what power gives you 1? 0. Right? So the numerator is approaching. Well, careful. The numerator is approaching the natural log of 1, which is 0. Right? 0. What's the denominator approaching? 0, because 1 over infinity is approaching 0. So this is 0 over 0. Yeah? So we have indeterminate form. And we have a fraction. Right? So now we can use L'Hopital's rule. Right? I think I'm going to go up here and rewrite this just because our friends online won't be able to see it. Okay, so now I just rewrote that, right? So what are we going to do? To use L'Hopital's rule, now what do we do? Find the derivative, right? So we take the rate of change. So the derivative of the top, ooh, baby. The derivative of the top is going to be 1 over 1 plus 1 over x times the derivative of the inside. And what's the derivative of 1 plus 1 over x? 1 plus x to the negative 1. That's what it is. So what's the derivative of that? Negative 1 x to the negative 2, or negative x to the negative 2? Over, and what's the derivative of the bottom? Same thing, we just did it. It's kind of nice how that worked out, yeah? So now, look at this. What happens? So now I have the natural log of L is the limit as x goes to infinity of 1 over 1 plus 1 over x. Okay, so now we've executed L'Hopital's rule, and now we evaluate the limit again and see what happens. If we have indeterminate form again, we do L'Hopital's rule again, right? What happens here as x goes to infinity? What's this approaching? The numerator is approaching 1, and what's the denominator approaching? 1 plus 0, right? So the right side of this, their picture. So long, farewell. Logan! So the right side of this, after I compute this limit, what do I get? What is this right here? The limit, this right side is approaching 1, right? So that's 1 there. Now that's not the answer to the problem. Because if you remember, the answer to the problem was L. And what we just solved for was the natural log of L. Right? So how do I figure out what L is? The natural log of L equals 1. So what's L? What does the natural log of L mean? E to the first, this means L is the E to the first, right? And there you go. That's what we thought it was, said it was going to be. Okay? This limit that we started with is E. Oh, this is going to make me cry. Okay? This is going to make me cry. So the natural law, the square root of 20. What is that? Tell me what you're doing. Like, what are you're thinking? I see your eyes going on. Like, tell me what's happening in your mind right now. You're trying to find a number that when you multiply by itself, you get. You're trying to find a number here that when you multiply by itself, you get 20, right? Yeah. So you're like 4, it's bigger than 4, but less than 5, right? You can ballpark that, right? So if I said this, the natural log of 9, can you do the same thing in your mind? Can you ballpark that? What does that mean, the natural log of 9? It means E, which is about 2.71828, so a little less than 3. E to what power is 9? So you can start to ballpark it, right? So 2.7 squared, it's more than 9's bigger than that. 2.7 cubed, well, that's going to be too big. So it's probably somewhere between 2 and 3, right? Like, but you understand the natural log of 9. So right here, if I tell you the natural log of something equals 1, that's basically saying that E to the first power has to equal to something. Because if I write this, the natural log of x equals y, that means E to the y equals x. Just like if I wrote the square root of x equals y, that means y squared equals x. These two things tell the same story. These two things tell the same story. Okay? But you have no problem thinking like this. I almost wish that, like, when you learn square roots, just forget it. Just learn logs instead. Because the way the thinking is the same. I mean, the thinking like the same, right? I mean, you have to just be able to think about the story two different ways. I mean, that's what you did here. You radicalized 20, and you're like, okay, what times itself is 20? But everybody gets logs, and they just have a panic attack. You know, it's just because you're. I don't know why we're scared of logs. Well, we are. I've been seeing people scared of logs for 24 years. And I myself was probably scared of logs when I was sitting in your shoes. Not literally, but well, in your case, yeah, you don't remember you lost your shoes that day of practice. Oh yeah, your shoes were stolen. Did she sweat in them and make them all nasty?
No, they're just gross to begin with.
Oh.
They're like
Okay, so questions on this. Do you want to do another one like this? Okay. Yeah. Okay, let's do. What time is it? What time do we get out of here? 21. And what time is it now? Okay. This marker's dying on me. So this is taking on indeterminate form. What? Which indeterminate form is this taking on? See if you can answer this without looking back in your notes. This is the one I gave you as the example, but how'd you get infinity, Megan? I see how you got 0. What's sine of 0? Okay. So this is 0 to the 0, yeah? So now how are we going to do this? Do you see how we have that function of x in the exponent? And when that happens, the common thing to do is do this logarithmically. Okay? So we set it up and we'll just say, well, all right, well, L is the answer I'm looking for. Okay? And now I'm not going to solve for L here. I'm going to solve for the natural log of L. So I natural log both sides, if you will. And then here's that little switch where I interchange the limit and the natural log. I lost my train of thought. There we go. I got it. Now, I probably should have some parentheses there, but I guess I don't have to. Okay, so what am I going to do now? Move it where, Will? Yeah. Okay, if you do these things logarithmically like this, if you do that, it is almost a faux show that you're going to use that property of logarithms where you bring down that exponent. It's going to happen every time. Okay. Oh, shoot. I need a fraction. What do you mean? Who said that? Becca. Becca said what now? See, she's thinking, I'm going to do this like I did the last one. So she says it's natural log of x over 1 over sine x. And can we, AKA 1 over sine x? Cosecant of x? Do you know that I taught for like 15 years before I knew what AKA stood for? Like that was an acronym. Also known as. And I just said it in class one time, like, and I made the connection in my head. It was like this big moment, like, oh my gosh. Yeah. What is what? What is TBH? Oh, is it to be honest? Yeah. I didn't know that one. Yeah. I mean, AKA has been around a lot longer than TBH, I think. All right, so let's check on indeterminate form, shall we? The natural log of 0. That's infinity, or going to infinity. Actually, negative infinity. Cosecant. Cosecant of 0. That's 1 over the sine of 0. The sine of 0 is 0, so that's 1 over 0. And 1 over 0 is approaching infinity. Okay? So it's going to be very helpful for you if you can tell me, like, what does 1 over 0 do? That goes to infinity. What does 1 over infinity do? That goes to 0. Like, if you can think that quickly, it's going to be very helpful. Why does 1 over 0 approach infinity? Like, think back to 5th grade when you learned division. Okay, when you learned about division, right? What happens when you divide by a smaller and smaller number after you get started to become a fraction? Like 1 divided by a half, 1 divided by a fifth, 1 divided by a tenth. Like, the quotient is going to get bigger and bigger and bigger. Okay? So 1 over 0 is approaching infinity. 1 over infinity is approaching 0. Okay? So this indeterminate form here is infinity over infinity. Okay? So can we lope this? Can we use L'Hopital's rule? I believe so. So got to take the derivative. What's the derivative of natural log of x? Yeah, what?
1 plus 1 over x. Wait. Yeah, 1 over 1 plus x.
The derivative of just straight up natural log of x is just 1 over x. I think you were giving me the derivative of the last one. Like you were giving me this. Like you saw that and just, yeah. So that's 1 over x. And then what is the derivative of cosecant of x?
Is it negative cosecant squared plus cosecant squared?
No squared. It's negative cosecant of x cotangent of x. Okay? So now, we probably want to try to clean this a little bit and see if some things simplify. Maybe. Well, isn't this the same thing as this? Okay. Uh-oh. So, so I'm just rewriting this. It's a hot mess right now. So that's cosine over sine squared, right? You guys agree with that? Okay. So notice I'm not doing L'Hopital's rule yet. And then realistically, that's the same thing as what? If I do 1 over x times negative the reciprocal, right? So that'll be negative sine squared over cosine squared. Is that right? Oh, sorry, it's not. Thank you. Cosine's not squared. You're right. So that'll be negative sine squared of x over x cosine of x. So what do we do now? Can we take the limit? What if we take the limit? What's as x goes to 0, what's the top going to? 0. What's the bottom going to? 0 times 1, right? Which is 0. So we're still 0 over 0. Crap. Can I say that online? What do we do now? So I think at this point we have 2 options. Okay? The first option is just continue doing what we're doing. Use L'Hopital's rule again. Okay? Because we still have indeterminate form, so we can still do L'Hopital's rule again. The other option, which I'm not necessarily willing to throw in the towel yet, the other option is sort of throwing in the towel, and it's going back right here. And when Becca so geniusly said, oh, I'm going to write that as natural log divided by cosecant, instead doing that as sine of x divided by natural log of x to the -1 power. Do you guys see that? So those are our two options, to continue on where we are here, or to go back and rewrite it here. Okay? Now, at this point, I think it's probably 6, 1/2 dozen the other. Because to do L'Hopital's rule again, right here, this bottom one, we're going to have to use the product rule. Okay? And since you guys are having a test over derivatives, maybe we should just do that for fun, instead of going back here. So let's see what happens. So the derivative of the top, I hope that you can take the derivative of sine squared in your head. I hope you can say that's 2 sine of x times cosine of x. Okay? And it's negative because that's where the there was a negative floating in there, and I just ended up with them in the numerator. Okay? All right, it's the denominator. Can we take the derivative of that? The derivative of the first, 1 times the second, cosine x, plus the derivative of the second, negative sine of x, times the first, which is x. Oakley dokie. Okay. Ready? Can we evaluate this? The numerator is approaching, as x goes to 0, what's happening to the numerator? Sine of 0 is 0, cosine of 0 is 1. 0 times 1 is 0. Oh, baby. This is scary. The denominator is approaching. The cosine of 0 is 1, plus sine of 0 is 0 times 0, 0. 1 plus 0 is, oh, why am I excited? Because I don't have indeterminate form. I have 0 divided by 1, which is 0. So limit this, timeout. Yeah. What am I offended by right here? My notation is bad. Because this right here, the 0 over 1 should have been up here. Like by putting limit and then 0 over 1, I already did the limit, right? So 0 divided by 1 is 0. So now, Megan, I shouldn't have called your name because now the whole world knows I called on you. I mean, my 1 million YouTube followers. What is L? Because 0 is not the answer to this problem. The natural log of the answer to this problem is 0. It's what? Which is 1. So the answer to this problem is 1. Okay? So in this problem, 0 to the 0 ended up approaching 1. Okay? And we lucked out. We didn't have to go back. You know, if this would have resulted in indeterminate form again, I probably would have thrown in the towel and said, let's go back. But thank goodness it didn't because we wouldn't have had time. Okay? So questions on that? God, no. This is not going to be on the test. Oh, well. I just told you, I had the test in my hand when I at the beginning of class. Yeah, don't freak out. Heavens no. That would just be mean. Like, yeah. Oh, we didn't get to play the song. Oh. Can I get 30 seconds?
Like, it's just so beautiful. You really need to see the words.
Is there like a dance number to it, or is it just
It's just a song. I'll link this so you can listen to the whole thing.
Every now and then I get a lemon that's confusing. It's some kind of indeterminate form.
Every now and then I get a little bit terrified. I think of arms.
All the time, beyond. That's monarchy day.
Listen.
So we take the rate of change of the topic of the fun. We don't need to rearrange. We're just going to heaven. And I know making it strange. Cause we take the limit again. If we find that we cannot define our limit, then we'll have to go with it one more time. The song's always works, but if you're in the dark, an oscillating function may be making it dark. And then the song doesn't work.
But most of the time, well, it does. Most of the time, our song
Once upon a time, I had trouble with math, and now they all
This
think
is
that I'm
fast.
smart.
Oh, like 10 times faster. Changes, slides across the line.
I just saw it on Instagram. They canceled Max. So come and walk with
They canceled YS. Yeah, that was the first thing that got canceled back in the spring. Was
Yeah,
YS.
the first show part, the other one part, it's not until August.
I cried on that. Did you get cry for your part? I bet.
Yeah, I really just saw it. I was like,
Why do you look like you're smiling about this?
I'm not
Your eyes are smiling like you're happy or something.
Well, that's just the.
It's craziness.
I'm just kidding, Rachel.
There were,
Anna Sarmer!
there were some kids on our team that got national cuts on Saturday.
You're kidding me. Wait, Sarmer, were you here yesterday?
Yeah.
Why?
Oh, I had to help him with the club. We were
That's the only reason you were for club?
Yeah.
I thought maybe you had to show up for classes too. I was like, that.
Oh no.
Okay. Oh. You just got your picture taken.
Yep.
And you wore a flannel for it?
Yeah. I do
That
it
is-
every year actually.
Do you really? You
Yeah.
wear flannels for your picture every year?
Yep. It's a tradition now.
Nice. See, she knows what's going on.
Man, we're sucking down the coffee here. What's
Well,
going
remember, Molly Merrill came in and got a cup this morning. It was a pretty large mug. I know.
The charity that we're running here.
We do need to stop. We
We're
need to-
live on the internet here, so don't want to say anything inappropriate.
Yeah,
Talk
we do.
about
We need
anybody.
a coffee sign back here, by the way. Like, we do need a coffee house. What should this coffee house be called? Like the Calc coffee house, or
Yeah, that's good.
we need some kind of a math coffee house name. You guys need to think of one for him.
Hello, everyone. We get our Are you guys being quiet?
I'm scared of the microphone right there.
No. This is the smaller class. Let's say there are like 20 some. Right now there's 4 people. I love though that like, so last period when we were doing this, and I'm just running one chat or one live. It's stupid to stop it. I mean, since you guys are back to back, but Noah Beeman's answering questions. Like when I had asked, he's answering questions in the chat, and you did it yesterday too. And I'm like, I have no clue what's happening in that chat. Like it's so small. I have to run this through my Chromebook because not one like the USB ports on my computer are all like just garbage. So, yeah. Did the bell ring? No, that wasn't the bell.
Students with the last name T-U-D that are in grades 9, 10, and 11 that are currently sitting in each or physical unit.
Last period, Logan, he was a senior, just got up and walked out. He wasn't. Forgot that he was a senior. Your picture. So, how's everybody doing? Yeah. 7:46. I slept in myself a little bit this morning. I can't seem to get a good temperature at night sleeping. Sometimes I'm cold. Wow, impressive. So I have your test. You guys are taking a test on Friday. So I have this in my I have that in my hand right here. So I figured I would give you some deets. Is that right? Deets. So you're gonna have 4 straight up derivative problems where you just find the derivative of something. I give you a function, take the derivative. Okay. You're gonna have 4 of those. Then you're gonna have 1 implicit differentiation problem. Okay. You're gonna have 1 related rates problem. That's a very easy related rates problem. Like, it's probably about as easy as they can get. And if you need the formula for the particular situation, I will give it to you. I might shame you publicly, but I'll give it to you. I won't shame you. Then you're gonna have 1 problem. See, the problem with this little mask plastic thing, you guys, I told you about this, is that when you have to like scratch your nose, it kind of looks like you're picking your nose. Then you're gonna have 1 problem where I give you a function and then you algebraically have to find the local maxes and mins and the inflection points. Okay? And it's a pretty easy function to with. Like about as easy as they get when it comes to doing those types of problems. Okay, it's a polynomial. And then you're going to have one problem where I give you the graph of a derivative. See, like there's a derivative graph. And then I ask you a bunch of questions about the function. Okay? You will have to know how to find the equation of a tangent line on this test. A lot of us like just fumbled around with that back in, I don't know, what do I want to call that? The fall, I guess, or earlier in the year, a few weeks ago, I don't know. But a lot of us fumbled around with that. You will have to know how to find the equation of a tangent line. So, and that's it. So those people that are going to be taking this test who are not here, I have to figure out how I'm going to deliver this to them. I might literally deliver it to them. I might just take it to their house. Because I only have, I mean, it's the number of kids that I have would have to deliver it to. I only think I have like 5. So, yeah. So, question? Oui? No? Did I clean your desks? Okay. All right, well, this microphone catches all of my drinking and bodily function noises. I don't know how many of you guys heard me burp yesterday in the middle of.
I heard you mention it, but I didn't hear it.
Yeah. I showed the live stream video to my family yesterday at dinner, and my wife's like, I can't read that board. How can you, how can they read that? So then I made it bigger, and she's like, okay, maybe that's a little better, but I still can't read that. And I said, I don't think you can read it because you can't read it. Like, she didn't know what it was saying. You know, if that would have been written in like Greek, you would say, I can't read that. Like, I can't see that very well because you don't know what it says. But I think if you know what it says, you know, I don't know. But, what else? So yeah, we'll keep doing the live stream. It seems like it worked pretty well until we go back online, which I'm predicting is going to happen.
School Friday.
Hey, you get out May 8th and fourth quarter midterms is May 6th.
Yeah, that's going to be an issue for us, AJ. I don't know, that's something that I've been like sort of stressing out in the back about in the back of my mind. I mean, it's not really in the forefront of my stresses, but it's definitely something I've thought of, because there's no way we're going to finish this class before May 8th. Like, no way. And I mean, no way. So I don't know what we're going to do. Like, you know, in the past, I've had kids come back just to take the exam for second semester, because, you know, you have to take an exam in here second semester. Yeah. But now that might end up being online. I don't even know what to tell you. But yeah, so May 8th, I don't know. I'm just going to keep pretending it's not true and think about it later, I guess. But that stresses me out big time. Because, I mean, I can't see us really finishing this class before, like, May 20th. Based off of the fact that we're not even starting second semester until the end of January. Like, so, I don't know. But, you know, you just got to roll, you know. It's 2020. You just got to roll. Roll with it. Okay, so if you watched the live stream yesterday, you saw that we learned L'Hopital's rule. And as you were coming in, you might have heard the song playing, which I'll play for you at the end. If you watched the live stream, you heard me talk about the song in Calculus the Musical. If you watched the live stream for this class, I think I talked about it in fourth period yesterday. But so what is, we use L'Hopital's rule to find limits when you have a limit that's in what form? What do we call it? Indeterminate form. And L'Hopital's rule only works, there were 7 indeterminate forms, and L'Hopital's rule only works for 2 of them. Which 2? Infinity over infinity and 0 over 0. So if you ain't got that, if you don't have infinity over infinity or 0 over 0, you can't use L'Hopital's rule. You've got to manipulate your thing to make it. Hey, Kazon, would you do me a favor? I just noticed that that burner is turned on, and that thing's going to start like burning. Flick that. Yeah, thanks. I mean, I already have some fire marshal problems here. I don't need any more. So you have to do some algebra to manipulate your situation so that you can get your function or expression into a fraction. Okay, and so what I'm going to do with you today is do 2 problems where that happens. Okay, and then your homework is going to be to do these sections from 4 point whatever it was. I think it's 8. Okay, they're on Google Classroom, and I'll probably even post them again after this period. And again, this is not on the test, so like, you know, you most likely are going to be studying for the test over the next few days. I get that, but just as a target, you know, I would try to get that done by Wednesday. Then, you know, yeah. So.
Can you do a Google Classroom post about what's going to be on the test, like the different?
I just told you.
I know, but
because you sat there and didn't write it down, like you want me to retype it up. Just watch it. Like, I just literally went over that with the test in my hand, and you sat there. Anna wrote it down, or she wrote down what she wanted to write down. Did you write it down? Come on. Huh?
I saw the dumb school supply shopping. I've been busy.
That's. I'm not even gonna respond to them. Who was the one that did somebody in here get a car recently? I remember having a Zoom meeting with somebody and they were getting a car. I can't remember who it was. And so maybe they're watching at home. I don't know. Oh, goodness. So let's do this problem here. So there's our problem. So if you go back and look at your notes, you'll see that this was one of the examples that I set up yesterday. But don't look, because I want to see if you can figure this out now. What indeterminate form is this taking on? As x gets huge, what is this thing, what form is this, like what is it approaching? Noah? Not, yeah, no, Noah. It's Noah. Yeah, I started doubting myself. Oh, you're telling me the answer. I don't want the answer. You're right. The answer is E, which we're going to algebraically prove that here in a second. AJ, what is it? 1 to the infinity. Because this is going to 0. Yeah? So 1 plus 0, 1 to the infinity. Okay, so this is approaching 1 to the infinity. Okay? Now, it is correct that the answer to this limit is E. Okay, but like as far as you know, I just pulled that out of my butt yesterday and told you that. I mean, you don't know where that came from unless you really did some hardcore investigation about the natural number E in your Algebra 2 and Pre-Calculus class. Like, because E comes from continuously compounding. Like, I mean, if you really got into, if you did some hardcore investigation of that, you might have gotten this, but I doubt it. Yeah.
Is it because, like, for the 1 over x, it's not actually getting to 0?
It's approaching 0.
It's approaching 0, but it's not actually getting to 0?
Well, yeah.
Which means the number is going to be...
I don't think you necessarily need to worry about whether it gets there or not. Just think the fact that it's approaching. You know what I mean? Because in this case, we're not really concerned whether it gets there or not. We're still just doing a limit here. What happens? What's it approaching? Okay. But 1 over x, it will be very helpful for you if you can tell me like 1 over infinity goes to 0. 1 over 0 goes to, like if I'm thinking about 1 over x, if x is approaching infinity, this 1 over x goes to 0. If x is approaching 0, 1 over x approaches infinity. It will be very helpful if you have those two ideas straight in your head. Okay? Like 1 over infinity is 0, 1 over 0 is infinity. And I use the term is very loosely. Okay? All right. So the rule here is, or the deal is in order to use L'Hopital's rule, we got to get this into a fraction. So we got to do some serious algebra manipulation to get this into a fraction, okay? Now, here's a little trick that's going to happen when you're doing a limit problem where you end up getting x's or some function of x in the exponent, okay? If you remember back when we learned about derivatives, I might have taught you logarithmic differentiation, okay? Remember logarithmic differentiation? They were horribly ugly derivative problems. But the idea of logarithmic differentiation is very similar to what we're going to do here, okay? I'm going to say, I don't know the answer to this problem. I'm going to just say that the answer to this problem is L. And why do I use L? Convention. Okay? I guess I use L because limit. All right? That's where the convention comes from. So I'm going to say, I don't know what the answer to this is. I'm just going to say the answer is L. All right? And then I'm going to solve this problem not for L, but the natural log of L. So I effectively take the natural log of both sides of this. Okay? And then if you think about this for a second, this probably will make sense. If I'm taking the natural log of all of this, okay, whatever this is approaching, I'm going to take the natural log of it. That is equivalent to taking the limit of the natural log stuff. Like interchanging those is equivalent. Okay, now it's only equivalent because the natural log function and 1 plus 1 over x and all that, everything's continuous after 0. So that's the only reason why that works. Okay? But now, here's why we did this trick. It's the same reason we did the trick when we did logarithmic differentiation. What can I do with this x? I can bring it down, use the property of logarithms. Okay? So now I'm sitting there. Now, right now, it might be worth a check to see, do we still have indeterminate form? We should. Okay? If we don't, we probably fouled up somewhere. Okay? So as x goes to infinity, what happens here? That's infinity. And as x goes to infinity, what do we have here? The natural log of 1 plus 0, or natural log of 1. What's natural log of 1? Now, I cried over the internet last period because they couldn't tell me what the natural log of 1 was. And I might cry for a second time today over the internet for the 100 million people that are viewing this right now globally. The natural log of 1 is 0. Because e to the 0 is 1. Okay? So this is infinity times 0. Is that indeterminate form still? Yeah, it is. Okay, so we're good. But now, in order to use L'Hopital's rule, I have to have a fraction. Right? I ain't got no fraction. So what did we do yesterday when we were faced with a similar situation? What did we do to rewrite that as a fraction? You remember? We rewrote this to what? Right. Yeah. So we wrote it like that. Okay, now we got a fraction. Okay? And notice, now we have, who said that? AJ? Now we're looking at 0 over 0, which is still indeterminate. Okay? And that's one of the reasons why, guys, infinity times 0 is indeterminate, because when you rewrite it, it could end up being 0 over 0 or infinity over infinity, like depending on how you rewrite it. Okay? So, I mean, if we would have written this x and then flipped this one, then it would have been infinity over infinity. All right, so let's rewrite it up here for all of our YouTube fans. Do you think I could start making money from this?
You have to put a number of subscribers.
You have to have at least 1,000 followers or subscribers.
I mean, I guess I am making money. I'm getting a paycheck. Okay, so ready? So now we're going to do L'Hopital's rule. I just rewrote, just for the ease of reading this. So let's do L'Hopital's rule. So what's the deal with L'Hopital's rule? What do we got to do? Find the derivatives of the top and of the bottom. Okay? And we treat them individually, right? Not the quotient rule. So this problem is now equivalent to, what's the derivative of the numerator? What's the derivative of natural log of 1 plus 1 over x? Well, it's 1 over 1 plus 1 over x times the derivative of the inside, and the derivative of 1 plus 1 over x, you got to kind of think about what's the derivative of 1 is 0, but what's the derivative of 1 over x, Samuel?
Negative x to the minus 2.
It's negative x to the negative 2. Okay? And then divided by, what's the derivative of the denominator? Samuel just told you. What's the derivative of the denominator? Negative x to negative 2 again. All right. Oh, look at this, friends. And so now, can we compute this limit? We got to remember, we don't keep loping. We stop and evaluate. What happens if I evaluate that as x goes to infinity? What am I going to get, AJ?
I'm sorry, I was looking at the derivative.
Oh, you have a question?
No, I figured
Oh,
out.
okay. What am I going to get if I evaluate this, if I make x go to infinity? What's the numerator going to do?
1 over 1.
1 over 1 plus 0. 1 over 1 is 1. So this right side is 1. That's not the answer to our problem. It's the natural log of the answer to our problem. Yeah? So if the natural log of L equals 1, what's L? E. Is that what you're going to say, Samuel? E to the first, I guess, right?
Please pardon the interruption. Students 9 through 11th grade would like the
It's so funny to me.
currently sitting in a south or west.
Is that you guys?
Classroom. Please make your way down to the auditorium for pictures.
It's very funny to me, our fear of natural logs.
For west classroom, please make your way to the auditorium for pictures.
I think some of us are more afraid of natural logs than we are of coronavirus. Like, And it's just so funny because if I said to you, now, what's the square root of 20? Could you ballpark it? No, I don't want 2 radical 5. I want the square root of 20. I just want to give me a number, a decimal. Could you ballpark it? Everybody in this room could ballpark that. It's bigger than 4 and less than 5. How did you get that? Because you looked at this and said, I'm looking for a number that's when I square it, I get 20. Right? Now, if I said this, what's the natural log of 9? Could you ballpark it? Why not? It's the same. It's the same line of thinking. It's the exact same line of thinking. You just have to think. Thanks, kid. You just have to think. E, which is about 2.718. E to what power is going to give me 9? Well, 2.7. If I square that versus cube that, if I cube 2.7, that's going to be too big, or is it? Yeah, because 2.7 is almost 3, right? 3 cubed is 27. Okay, we can shut that window. I don't want to walk over there because I'm not sure if I'll trip on the microphone. So the natural log of 9, you almost blew away there. The natural log of 9 is somewhere between 2 and 3, right? It's just a shame that we don't like think about logs that way. We just think logs and we just, oh God, logs. I suck at those. Okay. If you understood logs like that, this wouldn't be an issue at all. You would just know that. Or the natural log of 1 is 0. It would just be automatic. You would know that. Okay. Question? Est-ce que vous avez des questions? Non? C'est bon? Okay. You want to do another one? Some what?
The lunch yesterday, people were like taking pictures of it, and it was literally just like a pile of beans.
Guys, we got 8 viewers right now. There's a pile of beans?
It was just like beans with like a lot of water, and it looked bad.
I walked by and saw people eating corn dogs.
Yeah, but like in the corn dog, like there was corn dog, but then there was like a thing.
Oh, that was the side.
Yeah.
Oh, I love corn dogs.
Corn dogs are good, but like.
I mean, especially
Water beans.
Water beans, no.
Yeah.
But now I have a little caveat with a corn dog. Okay, if you buy frozen corn dogs, you're not sticking that thing in the microwave. You are not sticking that thing in the microwave. How are you going to make that? You're putting that in the oven or an air fryer. It's got to have the crisp. A soggy, mushy corn dog that was cooked in the microwave.
You might as well just eat a hot dog at that point.
Exactly. Just get a hot dog and put it on a bun.
Yeah.
Come on. We just got one like this weekend. Yeah, it is magical. Might have to make a mental note of that. My 7th grade daughter, Kate, made some like air fried, like she took these like doughs and wrapped them in cinnamon and sugar. It was like a churro. Oh, it was delicious. I really like to get a microphone that I could just stick on that camera and it would pick everything up. I thought this one would. When we did our calls back in the spring, earlier in the year, the mic was not connected to me, and when I would walk away from the computer, you could hear me, right? When I would walk away from the board, or I'd go like leave the room and go get coffee or something, you guys could hear me. Yeah, I don't know. Okay, so don't look at your answers, or not your answers, but don't look at your notes from yesterday. What indeterminate form is this taking? This is a key thing. This is half the battle of L'Hopital's rule, is being able to recognize the indeterminate form. Okay? What indeterminate form is this taking? 0 to the 0. Does everybody see that? Okay? 0 to the 0. So this means L'Hopital's rule is going to come into play. We got an indeterminate form. However, we can't use L'Hopital's rule until we got a fraction. And we can't even think about getting a fraction until we get that sign of x out of the exponent. And the way we're going to do that is logarithmically. So we're going to say, all right, well, I'm going to say that L is the answer to this problem. Okay? L is the answer to the problem. Okay. Now what do? Well, I'm going to solve for the natural log of the answer. So you guys would say, well, just log both sides. Okay, all right, fine. And then here's that little, I don't even want to call it a trick, but it's something that we're allowed to do because of continuity stuff, is that the natural log of this limit as x goes to 0, it's equivalent to doing the limit as x goes to 0 of the natural log of x to the sine of x. And you could probably see that if you just stepped aside from this problem and evaluated that limit, and you could see how they would be equivalent. Okay, if you thought about it this way and you thought about it this way, you could see that they're going to be the same. All right. Now what's our next step? So bring down that sign. Okay? Now, friends, what am I going to do here? You've got to get a fraction, right? Let's check our indeterminate form real quick. Sine of 0 is 0. Natural log of 0 is negative infinity or infinity. So we have 0 times infinity. So we are indeterminate. Question?
No, I think I have a.
Oh, you have an idea?
Yeah.
What's your idea?
The natural log of x over the cosecant of x.
Is that what your idea was going to be? Noah?
I didn't hear what you said.
He said natural log over cosecant. I'm just curious. There are two ways that you could have written it. You could have done sine over natural log to the negative 1 power.
I was thinking natural log over 1 over sine, but that is cosecant, right?
Yes. You could have done it like this, or you could have done it like this. Okay? Which this right here is cosecant. Okay? So, because I worked this out last period, I know the second one works. So we'll do it that way. Okay? But we will kind of run into a little bit of a snag. Yeah.
The natural log of x, plug in a 0. How is it infinity?
How is the natural log of infinity 0?
No, how is the natural log of x infinity?
It's approaching infinity. If I go to the natural log of 0, if that's what I'm thinking about, the natural log function, okay, let's think about this algebraically and analytically, graphically. Like, the natural log function, if you think about the graph, looks like this. It has a vertical asymptote at x equals 0. As you approach 0, it's going to negative infinity. Okay? Why is that? The natural log of x. Okay? Well, you can't log 0, but why? Why can't you? Don't just tell me you can't natural log 0. Because nothing, no exponent that you put on e is going to give you 0, ever. Okay? But what happens if you put a smaller and smaller exponent on e? Like, for example, e to the negative not negative. I was sorry. Like, what's I got this backwards in my mind, and now I can't get. Now I'm stuck in a. I got to rethink. Hold on. There's no exponent that you can put on e that will give you 0, correct? That's why natural log of 0 doesn't exist. But why does the natural log, as x goes to 0, approach negative infinity? Like, what's the natural log of 1/2? Or say, what's the natural log of 1/100? Okay? What does that mean, the natural log of 1/2? E to what power is going to give you 1/100? Or e to what power is going to give you 1/2? Right? How does e get really, really small? What exponents do you have to put on e that make it really, really, really small? Numbers that are approaching 0. Think about e to the x. There's e to the x, right? As x gets really to negative infinity, what's happening to e to the x? It's approaching 0. That's why the natural log of x, as x goes to 0, is approaching negative infinity. Okay? All right. So we happy here? Still got indeterminate form. What indeterminate form do we have? Infinity over, the cosecant of 0. That's 1 over the sine of 0. That's 1 over 0, which is infinity. 1 over 0 is infinity, right? So we have infinity over infinity here. Cosecant has a vertical asymptote at 0. Cosecant has vertical asymptotes at 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. Okay? So now, we'll do L'Hopital's rule. Ready? So what's the derivative of the natural log of x? It's 1 over x. And what's the derivative of cosecant of x? It's negative cosecant of x, cotangent of x. Okay? So I'm just going to stick the negative there. Doesn't matter where we stick it, since we have all multiplication there. So let's see if we can clean this up, yeah? You want to try to clean this up? So before we try to do L'Hopital's rule, let's just do some little housekeeping. So I have negative 1 over x over, secant is 1 over sine, and cotangent is cosine over sine. So this is cosine over sine squared. So I have negative 1 over x divided by cosine x over sine squared of x. Right? And then that's going to be sine squared of x, I'll stick the negative there, over x cosine of x. Okay? So I had to put on some algebra pants here. I mean, it's definite algebra pants. I mean, it's definitely algebra pants season. So can we evaluate this now? What happens as we go to 0? The numerator is going to 0. What's the denominator going to? 0 times 1, which is 0. Dang it. Still indeterminate form. Okay? So at this point, you have two options. And it depends on how quickly you are willing to throw in the towel. Okay? One option is to just keep proceeding and do L'Hopital's rule again. Totally legit. Another option would be to go back to right here. And instead of writing it the way we wrote it, which was like this, redo the problem like this. Okay? You following me? Now I know it works if we do it the other way because we did it last period. Okay? And I think that this derivative is not too hateful to do. So let's do L'Hopital's rule. What's the derivative of sine squared? Okay? I think you should know how to do that. And I would almost be able to do it in my head. Okay? It's 2 sine of x times cosine. Okay? Now, what's the derivative of the denominator? It's a product rule there, friends. There's a product rule there. That's x times cosine of x. So we've got to use the product rule. So it'd be the derivative of the first, 1, times the second, cosine, plus the derivative of the second, negative sine of x, times the first, x. Okay. So now, friends, can we take the limit? What happened to the numerator as x go to 0? Sine of 0 is 0. Cosine of 0 is 1. It's sometimes you got to remember that 0 times 1 is 0. Like, you get caught up in these indeterminate forms, and you're like, you forget the basic stuff. 0 times 1 is 0. Okay? So this numerator is approaching 0. The denominator. Cosine of 0 is 1. Sine of 0 is 0. 0. 0 times 0 is 0. So the denominator is approaching 1. And 0 divided by 1 is 0. So the right side is 0. 0 is not the answer to our problem. 0 is the natural log of the answer to our problem. So the answer to our problem is e to the 0 is 1. Okay? All that for 1. And all that for 0 to the 0 actually ended up being 1 in this case. Okay? Kind of annoying. But it's okay. Question? Jack McAfee said 1. He chatted 1. Now that he could have been answering a question from 45 minutes ago, but he just chatted 1. So, that's an example of how you use L'Hopital's rule when you don't have a fraction. Okay, these 2 examples of you doing it logarithmically. And you're going to do that if you have functions of x in the exponent. Yes, Sam? So, I think I understand your question. Like, if we would have had an indeterminate form here, could we have done it again? Is it possible that you could just keep doing this over and over and over again and just go in circles? Yes. Am I going to give you a problem like that without telling you ahead of time, or like, I'm not going to give you a problem like that where I'm assessing your knowledge of L'Hopital's rule and I throw you into this endless circle. Like, now, could we have a situation where we investigate something like that? Absolutely. They have names for that. It's like an oscillating function. In fact, that actually is addressed in the song from Calculus the Musical that you guys heard when you're coming in. I will link this on Google Classroom so you can go and play it for your family. So Calculus the Musical is a bunch of songs about calculus that are parodies of other songs.
I think you're.
You guys, what? It is Total Eclipse of the Heart.
Yeah, exactly. I think you're without thinking of diary won't be good.
Beautiful. You guys can go.
Now and then I get a little bit of trouble when I'm taking a minute. Every now and then I get a limit that's confusing in some kind of indeterminate form. All the sun beyond what the murky day. be enough. So we take the rate of change of the top and of the bottom. We don't need to rearrange. We're just going to compare them. And I know that we're making this strange, cause we take the limit again. If we find that we can't define our limit, we will have to go repeat one more time. It's almost always works, but if you're in the dark,
Daniel, this is what you were talking about.
But most of the time I sit down. But most of the time I saw. Once upon a time I had trouble with math. Now they all think that I am smart. There's nothing I can do. I have calculus in the heart.
Once upon a time I was crying all night, but now I do my math in the dark.